Hello, this is Galen Pickett again, Cal State University Long Beach. This is Physics 151. We're still talking about Chapter 1, and now I want to talk about Section 1.8, Momentum. So, momentum, there's the section you should be reading. In the ebook, again, in the physical book, you can take a look and see what that is. Momentum is an extraordinarily important quantity. It describes the amount of motion that a system has got. It's a physical quantity that a system has, and how a system gets this momentum and how it interacts with its surroundings to get this momentum, that is the big topic of Chapter 2 that's coming up. But first, just what is momentum? So here I've given you a picture of an object that is being thrown at you from me. So here's the first object, the one on the top. Here's the second object, the one on the bottom. The only information you have are these dots showing you where is the object at equally spaced time intervals. So I know that these objects are moving without any interaction once I launch them. The one on the top has got a very large delta r from one time to the next. The one at the bottom has a small delta r. So this one is going fast, and this one is going slow. And if I ask you which one of these two objects you want to stand in front of, that's the only information you have. You can stand in front of the fast object, you can stand in front of the slow object. And assuming that the two objects are the same object, then it's pretty clear what you want to do. You want to stand in front of the slowest object, because that is the one that you've got to interact with the least in order to bring it to a halt, because it's going to hit you, and you're going to be responsible for stopping it. I started it, you get to stop it. And if that's all the information you have, the velocity information is not enough. So I can tell you a little bit more about what these objects are. Let's say that this top one is a ping pong ball, and this bottom one is a car. And now that you know something about the objects, something about their identity, if this ping pong ball is coming at you at 1 meter per second, and the car is coming at you at 1/2 meter per second, you still may not have much of an idea which one you want to stand in front of. I'll point out to you that an easy way to calibrate this walking speed, well, a typical person like me can walk about 3 miles in 1 hour. That is a perfectly good measure of velocity. That is also about how often you can take steps. When you're taking steps at a normal pace, you do about 1 meter every 1 second. So 1 meter per second is about 3 miles an hour. So you have a ping pong ball that's coming at you at 3 miles an hour, or you've got a car that's coming at you half that speed, 1.5 miles per hour. And that is going to be hard to stop. You're going to need to work. We'll talk about what work is in an upcoming chapter, but I think you'd rather stand in front of that ping pong ball. A 3 mile an hour ping pong ball, you would not even blink at stopping. You wouldn't even notice that one's been thrown at you. The car, it's a significant challenge. So there's something besides the velocity that you need to know how much motion an object has got, and that thing is the mass of the car. So the mass of the object. So as long as the objects are going slowly, you take how much matter the object has got, that's in kilograms, and you multiply it by the vector velocity of the object. That's what I'm going to call the momentum of the object. That has conventionally got a symbol p to tell you, that's what a momentum is. Notice it's a vector that's in the same direction as the velocity. And this is for person through, say, planetary size objects that are not going very fast. Not going very fast, not fast. Not fast compared to what? Compared to the fastest thing in the universe, which is light. The speed of light, 3 times 10 to the 8 meters per second. That's how fast, as long as you're going much slower than that. And anything that is a baseball that's been thrown or caught or even launched from a cannon or shot from a rifle, launched from the surface of the Earth, that is true. Now for an arbitrary object, however, and we do routinely make objects go very close to this speed in particle physics experiments and accelerators, the actual expression which is known to be correct as long as that's known to be correct in every experiment in which it's been measured is the following. There's a factor that Einstein discovered that that depends on how fast the object is going times the mass times the velocity, the so-called gamma Lorentz factor. You can calculate it. It's 1 over the square root 1 minus v squared over c squared. So whatever the velocity of the object is, you compare it to the speed of light. Notice that this is dimensionless, has no dimensions, so the momentum always has got units in either of these cases. The dimensions of the momentum are kilograms, that's for the mass, times meters per second. So, how big is this gamma? Let's suppose we've got a 1 kilogram object that is going at 10 meters per second. What is the momentum? Well, the momentum is clearly going to be very, very close to 1 kilogram times 10 meters per second, or 10 kilogram meters per second. But that's assuming that gamma is exactly 1 for this object that's moving at 10 meters per second. Let's see how big the gamma really is. So gamma is 1 divided by the square root of 1 minus v squared over c squared. Now if you're going to take that 10 meters per second and then divide it by 3 times 10 to the 8 and square it and put that into your calculator, you're going to get exactly 1. So I'm going to use an approximation scheme that you will learn on this campus at Cal State Long Beach. It's a Calculus 3 topic. This is a Taylor expansion. If v squared divided by c squared is very, very small, then 1 over the square root is approximately 1 plus 1/2 times that thing which is small, v squared over c squared, and then I can add other terms which depend on v to the 4th divided by c to the 4th, and so on. If v is very, very small, those terms are going to be very, very small, and that's the only approximation I'm going to need. So my gamma factor here is 1 plus 1/2 times, my velocity is 10 meters per second, so I'll write that as 10 meters per second, but I have to square that. Then I divide it by the c, which is 3 times 10 to the 8 meters per second, and I square that. So I get 1 plus 1/2 times. The 10 squared is 100. I get meters squared per second squared. The denominator is, the 3 squared gives me 9. The 10 to the 8 gives me times 10 to the 16. And I still have meters squared per second squared. And I'm going to do this sloppy and approximate. I'm going to say that this 9 is approximately equal to 10. So I'm going to cancel this 9 and one of those zeros. So what I have is, my gamma is 1 plus 1/2 times. Now I have 10 divided by 10 to the 16. That would be 10 to the minus 15. And I can write that as 1 plus 0.5 times 10 to the minus 15. It's the same thing as 1 plus 5 times 10 to the minus 16. So I'm going to write that one down. 1.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then in the 16th place I put a 5. That is what the gamma is for this 1 kilogram object going at 10 meters per second. So the momentum, the magnitude of the momentum, is going to be 10 kilograms times 1, excuse me, it's 1 kilogram. We've got to make sure I got this done correctly. 1 kilogram times 10 meters per second times that thing, which is 10 point. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 kilogram meters per second. So as long as we have objects which are going with v much, much less than the speed of light, we are going to be able to get away with an approximate scheme saying that the magnitude of the momentum is just m times the v, the velocity. For an electron going near the speed of light, if the velocity of the electron is, say, 0.8 times c, the gamma is going to be significantly different from 1. It's going to be larger than 1. And notice how this approximation scheme works. It's always 1 plus something which is positive definite. The gamma is always greater than 1. If I take 1 minus something, the denominator is going to be less than 1. 1 over the denominator, gamma will always be greater than 1. And in fact, as v approaches c, gamma will approach infinity. So there is no way to have v equals c. That would require an infinite amount of momentum. And as we'll see in Chapter 2, the only way you can get momentum is from the surroundings. And the surroundings never have an infinite amount of momentum. So you can never actually get that. The speed of light is the speed limit for any material object in the universe.